Okay, so ray optics is the first chapter from your part 2 book, and to be honest with you, it is not a very difficult chapter. Um, like as far the legend goes, ray optics is very difficult. People say ray optics is very difficult. No, ray optics is not that difficult. Only thing is there are concepts that are very confusing, and they require proper attention from you guys. So one important thing first before starting anything is before sign convention as well, we need to understand what kind of lenses and mirrors can we have. So we can have a plane mirror, something like this, which if a light comes in, will go back at the same angle. So suppose this is the normal that is drawn to the surface of the plane mirror. And if this is the incident angle, the reflected ray will come out with the same angle. So I will be equal to R. The reflected angle will be equal to the incident angle. Okay, this is how a plane mirror works. And if it is 100% polish, so if the plane mirror has 100% polish, which means there is no light leaking out from the mirror to the backside, then 100% of the light intensity coming in as the incident ray will come out as 100% reflected ray, which is not possible. You can't produce 100% perfectly reflecting mirror. So, but if it was 100% reflecting mirror, then the 100% of incident ray would come out as 100% reflected ray. Okay, that would be one thing to know. Then what we can do is the next type of mirror we should be aware of is the convex mirror, right? Yeah, convex mirror. So if I have the reflecting surface, I mean the coating here and the reflecting surface on the inside, can you type someone whether this is a concave or a convex mirror? I think I have allowed typing. So if you know the answer, just type it down. Yeah, it's a convex mirror. You're absolutely correct. So one second. What did you say? Let me check your answers. So Gia is the only one who says this is concave. Gia is the only one who says this is concave, and she's the only one who's correct. This is a concave mirror, right? Do you have any doubts? Do you think I'm wrong? This is a concave mirror. That is for sure because it is caving inside. So if the inner side is reflecting, this is a concave mirror. Okay. So Gia is the only one who got it correct. I think I'll check the chat again. I think it is Gia. Yeah, Gia is the only one who got this correct. Upasna and Prashna were wrong with this, but yeah, all good. Uh, this is a concave mirror. This is a concave mirror, and in the concave mirror, if your object is placed, let's say, somewhere here, the light from the object will come and go past the focus. Okay, so they will discuss about this later, but right now we just need to know this is a plane mirror, this is a concave mirror, and there is a convex mirror which will look something like this. The inner side will be coated and the outer side will be reflecting. So this mirror will produce imaginary images. So the rays will be imaginary because the rays will go there. It'll go up and you have to produce it downwards like this. Something like this. Okay. You don't need to worry about this right now. But for now, you just need to know that this is a concave mirror and this is a convex mirror. Now, on the other hand, if you have a lens, let's say we talk about lens is something that is transparent. What kind of lens is this? I want you to answer this in the chat. This is a convex lens. Okay, Gia is correct. Upasna is also correct. And Prashna hasn't written it, but this is a convex mirror. And this is a concave lens. This is a concave lens. Right? Now, I'll mark 1 and 2 for these two. Now, my simple question is, which one of these two will predominantly produce imaginary images. Not real images, but imaginary images predominantly. Which one of these two lenses, one or two, will produce predominantly imaginary images? My simple question. Okay, Prasna says convex. Upasna says 1. Jia says convex as well, which everyone is incorrect. So it is completely different from the lens, okay? A convex, mirror. A convex mirror produces imaginary images, while a convex lens produces predominantly real images. Only there are few cases where a convex lens produces imaginary images. That will come later when we talk about the position of objects and images later, when we talk about lenses in detail. But now a concave mirror produces real images predominantly, but concave lens predominantly, not predominantly, almost every time, concave lens produces imaginary images. Because it's very simple to understand, because if you have an object here, the light ray will go here, and since this is concave, it'll just go away like this. And the two rays will never meet. So one will pass through the optical center like this. These two rays will never meet. So you have to produce them back and like make them touch somewhere here. So now you have an imaginary image produced here, not a real image. Okay, but if you talk about a convex lens, if you have an object here, I'm not scaling this to anything. Okay, I have not taught you focus or 2f or anything. But if you have a convex lens, sorry, one of the rays will go here and it'll refract back and go and pass through a point here. Then one will go here and touch. These two will touch here, and you'll find an image somewhere here. Now this image is real. So a convex lens predominantly produces real images, while a concave lens predominantly, or in the majority of the cases, produces imaginary images. Okay, not that difficult to take in. But you'll know about this and you'll understand this later when we do the position of objects and images in detail. But right now, I don't think you need to worry about it. Okay. So now we need to discuss about the 2 points in mirrors called focus and center of curvature. Okay. So we'll talk about focus and center of curvature. So focus is a very interesting term in lens and mirror. So focus is something where a parallel beam of incident light passes after reflection or refraction. So if you have a spherical lens or a spherical mirror, it doesn't matter. Let's take 2 cases, one of a spherical lens and one of a spherical mirror. So I'll take a concave mirror. I'll take a concave mirror and a convex lens. I'll draw this line. This line that passes through the center is known as the principal axis. This is known as the principal axis. Yeah, you want this one, focus, the definition of focus. Okay. So focus can be simply understood as the point on the principal axis of a lens. So you have a lens or a mirror, and the line from the center of the lens or the mirror is known as the principal axis. Okay, it is known as the principal axis of the lens or the principal axis of the mirror, right? So now focus is basically defined as a point on the principal axis where the incident beam of light, which is parallel to the principal axis. So if you have an incident beam of light that is parallel to the principal axis, this ray, after reflection or refraction, will pass through the focus. So this is for the convex lens that I showed. Now for the concave mirror, something like this, a ray of light is parallel like this. Now this ray of light after reflection will pass through a point. That point is known as the focus. Okay, so focus in simple term is a point on the principal axis where a parallel beam of light, which is basically parallel to the principal axis, will pass through the focus after reflection or refraction. Okay, so in this case, the light is passing through the focus after refraction. And in this case, it is passing through the focus after reflection. True? Can you follow? Okay. Upasana, what about you? Can you follow? Okay. Prashna, is this clear? I haven't seen. Okay, nice. Prashna is that. So okay. So this is how a focus works. Okay, focus is a point on the principal axis where a light beam parallel to the principal axis, incident light beam parallel to the principal axis, passes through it after reflection or refraction. Okay, it can be on any spherical mirror. So you can take mirror or lens. You can take a spherical mirror of any kind, or you can take a spherical lens of any kind. And if a ray of light is parallel to the principal axis, incident ray, then it will surely and like in after reflection and or refraction will pass through the focus. You should be very aware of that, right? Now, after defining focus, one thing is very interesting to understand, and one thing is very, you should be aware of this, is known as the focal length. So let's say this is f1, this is f2. So this is basically the focal length. It is the distance between the focus and the optical center. So this point at the center of the lens is known as the optical center. Optical center. And what you need to be aware of is the principal axis passes through the optical center. So this point lies in the principal axis. So principal axis will pass through the optical center. Okay. So F2 is also the distance between the focus and this point, optical center. Okay. So optical center is defined. Optical center is the point inside the lens where the principal axis passes. Okay. It is the center point of the lens or the mirror. It is the center. And from that point, the principal axis passes. Right. So focal length is the length between the point focus F and the optical center. In any case, in the lens case or in the mirror case. Can you follow? Okay, nice. Now, a new term can be defined after focus is known as the center of curvature. Center of curvature is a very simple concept to define and understand if you can follow. Just look at it. So if I talk about a lens, now let's talk about a convex lens again. So I'll talk about a convex lens. So basically, a convex lens is like two lenses which are placed like this. And this is a very big diagram, although a very small one. Nice one. So it is something like this. This is a convex lens, okay? But if you draw the full part of it, it is basically two circular lenses attached like this. So this is a circular lens. This is another circular lens. And they are just overlapping at this point, right? This point, they're overlapping. And when we cut out this shape, this becomes a convex lens. Okay. So we have a circular lens. So when I talk about circle, one thing is very important in a circle. So if you want to define circle, there is only one thing that can be used to define a circle completely. Can anyone write that on the chat? If you want to define a circle, there is only one term required. What is that term? Perfect. GI is absolutely correct. It is called the radius. So if you have a radius of a circle, you can imagine what the circle will look like, how big the circle is, right? So there is a radius between this point. So this is, let's say this is R1, and let's say this point is R2, right? So now I'll just erase this. This is very confusing. So let's say that these two circles have the same radius, okay? So I'm saying that these two circles have the same radius. Let the radius be R. Now, when you draw only the lens now, so if the same lens is only drawn, I'll forget about the circles now. And this is the principal axis again. and this is the part of this circle. This is a part of the circle. It goes like this. Okay. Now, center of curvature is marked as C on the principal axis. It is just the radius of the spherical mirror. I mean, the spherical lens. So this distance is the radius. Can you follow? Center of curvature is basically the radius of the two spherical lenses. Okay. And it is marked as C in the principal axis. And it'll be on either side, because there are two lenses, there are two spherical mirrors. So there will be obviously two radii. So there'll be two C's on both sides. And it is very important to know that these two circles have the same radius. R1 equal to R2 equal to R. So the radius of curvature, or the center of curvature distance, this will be equal on both the sides. Okay. So center of curvature is basically the center of curvature is the point on principal axis, which basically denotes the radius of the circular lens. Am I clear? Can you follow? Prashna and Upasna, can you follow? If you cannot follow, I'll explain with another example. So I'll give you another example. So I have, let's say, what kind of mirror is this? Concave or convex? Type it fast, quick. Okay, I'll do that. This is concave, correct? This is concave. There is a principal axis here that passes through the center. Now this also is a part of a circle, right? So this, if you can imagine, there'll be a circle like this. And from this circle, this small part is taken and made into a mirror. Now, if you have a circle, there will always be a radius, right? This point is let's say, the center of the circle. Now, this point in the principal axis is known as the center of curvature. Okay. Center of curvature is the point which is basically the center of the circle, where the lens or the mirror is derived from. So this is the circle where the lens or the mirror is derived from, and the center of this circle is the center of curvature. The name itself is very clear, I guess. Center of curvature. This is the center of the curve. So the curve here is a circle, and the center point is known as the center of curvature. And if you just think about it, this distance will be the radius. Can you follow? Upasna, is this clear now? Yes. Okay. Nice. Amazing. So this is this. Then one more thing, a very interesting thing that you can understand now is, if this is C and this is F, the focal length will be half of the radius. And this can be derived. I can derive this. I'll derive this as well. But for now, you can just remember that focal length is half of the radius of curvature. So this is known as the radius of curvature. So the focal length is half of the radius of curvature. I can derive this. I'll carry on with the derivation. If you write this, I'll do the derivation as well. Okay, so let's see how we derive it. I'll take a simple example of a concave mirror. Wait. I'll take a concave mirror like this. I'll draw a line at the center. This will be the principal axis. Very simple. This point. What is this point? Is known as the optical center. So I'll not draw this because it'll come in like the place where I need to draw something else. Now, this will be focus, as I already said. And this will be, let's say, the center of curvature. Now, I just need to prove that the focal length is half of the radius of curvature. So this is R. This is F, right? So now, let this point be let's say this point be A. This point is A. And what I do is I'll drop a perpendicular from this point down here. Okay, I'm dropping a perpendicular from this point here. Can you follow this? I'm dropping a perpendicular from A to, let's say, this point as B. Can you follow what I'm doing here? Yeah. So if this is a perpendicular, then this angle is 90 degrees. True? Yeah. Okay. If this is 90 degree, so if this is a perpendicular, this is 90 degree. Now let's say I draw a line, I draw a ray of light that is parallel to the principal axis. Where will the reflected ray pass from? Yeah, it'll pass through the focus, something like. Okay. Can you understand this? So now if I draw another line here, and if this angle, which one angle? So let's give you a very simple example. If this distance is 10, this distance is another 10. If this angle is theta, what will this angle be? I've written something that I need to check. No. Yeah. So can you follow this, what I'm trying to do? Yeah, it'll be theta. No, it'll not be theta. So if it was theta, then it would make a lot of issues. Theta minus x? No. No. Yeah, it'll not be 2 theta. Just think about it. So if you are very close to a tower, if you're very close to a tower and you're like a little bit away from the tower, so in which cases you need to see you need to stretch your head, you need to bend your head a little bit upward to see the tower more. Is it here or is it here? Is it 1 or 2? In which of the two scenarios you'll need to, yeah, for in one you'll have to pull your head back more, right, as compared to 2, which means which angle is steeper? Is this angle steeper or this angle, 1 or 2? Which angle is more steep? Yeah, 1 is more steep. So if 1 is theta, this cannot be 2 theta. This is not possible because 1 is already very steep because you are looking really upwards, right? You need to bend your head a lot upwards to see the top of the tower, right? So this cannot be 2 theta. So what will this be now? Since the distances are equal, this will be half of theta. Okay. If this was 2 theta, this would have been theta. Okay. So if I assume this to be 2 theta, this will be theta. Right? Can you follow? This derivation is not that important, but this is very important for you to understand now. So now if I take a right angle triangle AFB, if I take a right angle triangle AFB and apply tan 2 theta, what will I get? I'm taking triangle AFB and I'm doing tan 2 theta. What will I get? So tan is perpendicular by base. What is perpendicular? Yeah, it is AB. What is your base? Base will be FB. This is your 2 theta. Now let's do it for tan theta. Tan theta will be equal to, again, AB divided by CB. Yes or no? Yeah, true. So now for small angle theta, small angles theta, for small angle of theta, tan theta is equal to theta only. So here theta and 2 theta are small angles. So tan 2 theta can be written as just 2 theta equal to AB by FB. And theta can just be written as AB by CB. Now what I'll do is, I'll just make it as theta will be equal to half AB by FB. And here theta will be equal to AB by CB. So now my left hand sides are equal. I can just equate the right hand sides. Half AB by FB will be equal to AB by CB. I can cancel this off. So CB, I'll take CB to the other side. I'll bring 2FB to this side. CB equal to 2FB. Yeah, okay. From which part? From which part? Okay, 1 second. So I took this triangle AFB, where tan 2 theta, which perpendicular is AB, divided by base is FB. This is there. Then I took another triangle ACB, where tan theta is AB by CB. Okay. Now for small angle of theta, tan theta is theta. So tan theta will be theta also. Tan 2 theta will also be 2 theta. So your 2 theta will be equal to AB by FB. That is exactly what I wrote here. Okay. I just removed the tan here because for small angles, tan theta is theta only. And in this case, tan theta is AB by CB. I did theta equal to AB by CB. Now what I do is I rearrange for theta. So theta will be equal, this 2 goes to the denominator, half of AB by FB. So I'm just changing this equation here. Then here, theta is AB by CB again. Now we know that left hand sides are equal, theta, theta. So I can just equate the right hand sides. So the right hand sides are half AB by FB equal to AB by CB. Now AB and AB strike off. What you're left is 1 by 2 FB equal to 1 by CB. I take the CB here, FB here, CB equal to 2 FB. So now what is CB? CB is center of curvature to the optical center. So this will be radius of curvature, R will be equal to, what is FB? FB is basically focus to the optical center. That will be F, and there is 2 in front. So radius of curvature is 2 times focal length, or focal length is radius of curvature divided by 2, which satisfies the thing that I told you before. Am I clear? Now I want to know if you guys understood this or not. Especially Prasna, have you understood this? Yep, amazing. You got this. What time is it? It is 9:39. Okay. Now, let's learn the sign convention. Yeah, okay. I'll show you the thing here. You guys can take a moment to. You don't need to copy it. If you don't get time to copy, I will still upload this video on YouTube, so you can just take that. This is this. Then I'll give you 2 more minutes to copy this. Then what we'll do is we'll learn sign convention now. Then after learning the sign convention, I'll stop the class today there. Then tomorrow we can start. I don't know what happened to my Zoom Premium. This is automatically stopping the class at 40 minutes. I don't know. I'll fix that as well before joining tomorrow's class. Okay. If you've done copying, just let me know on the chat, please. Done? Prashna, are you done? Okay, amazing. Now the last topic for today is sign convention. I'll again use the blue ink. Very important to use this sign convention because it is universally accepted and used. So what we'll do is we'll just understand this in the mirrors, and we'll implement the same in lenses as well. Okay, we'll understand this in a concave mirror, and we'll try to implement all that we learned here in lenses when we start lenses. Okay, right now we'll just learn this in mirrors, and it's almost similar in lenses, so it'll not be a problem at all. So let's say this is my object. So let's say this is my object AB, and I assume that light is coming from here. This is the direction of light. Obviously, when my object is here, the direction of light will be along this, right? So this is the principal axis. So anything in the upper half of the principal axis is considered to be positive. So if you had to represent the height of this object, that would be a positive quantity. Okay. Everything above the principal axis is considered to be positive. So every height, object height, or even if an image is formed above the principal axis, that height of the image will be considered positive. Correct? Anything below the principal axis will consider to be as negative. Okay. For example, let's just do some experiment right now. So I say this is the focus, and there is a incident beam of light coming this way. Now I'll draw it using another color. So I have incident beam, something like this. We know that the incident ray that is parallel to the principal axis will pass through the focus. This is your reflected ray. Let the other ray pass through the optical center. So if it passes through the optical center, it will go back at the same angle. So your image is formed somewhere here. So I'll zoom it a little bit. So your image is formed somewhere here. So let's say your image is A dash, B dash. Now, my question to you is very simple. So if let's say if H1 was the height of the object and H2 was the height of the image in this case, which one would be positive? Which one would be negative? My simple question. Okay. And which one would be negative? So this is positive. Okay. GS says both positive. Prashna says only object. What does Upasna say? Go on. Okay. So it is very simple. What did Upasna say? Yeah, Upasna says both. Answer is both actually, because everything above the principal axis, if we have any height above the principal axis, will be positive. So in this case as well, the image is also above the principal axis because the image is here, right? So the image height will also be positive. So if H1 is the object height, if it is positive, image height will also be positive in this case because image is formed above the principal axis. So anything above the principal axis, any height above the principal axis is considered to be positive. Am I clear with the explanation? Why is the image positive here? Amazing. So if there are any height below the principal axis, we consider them to be negative. Okay. Okay. Now what we need to do is we need to understand one last thing, last part of the sign convention. I don't want to make this overcrowded here. So I'll do it again with another diagram. So the diagram is similar. You have a concave mirror like this. You have a principal axis that runs through the optical center, and you have an object here. Now, there is also a term called the object distance. We generally represent using alphabet U, not new. This is U, okay? It is not new. It is U. And there is another term called image distance, which we represent using V, okay? And these distances are measured from the optical center. So all these distances are measured from the optical center. Now, we know that the direction of light is this way. So light is going this way. So now, if we had to measure the distance of the object, we have to measure it this way, right? Starting from the object to the optical center, and this would be U, and it would be positive. Okay. Now suppose the image is formed somewhere here. We drew the image somewhere here, right? So in this case, we had the image here. So in this case as well, let's say the image is somewhere here. I'm not drawing the rays. I don't want to overcomplicate the diagram. This is the object AB. This is the image A dash B dash. Now for this, so now the distance is against the ray of light. So the rays are coming here and meeting somewhere here. And this distance has to be measured here. So since it is against the direction of light, light is moving this way, and we are measuring the distance this way, this distance will be negative. Am I clear? So suppose if I had image somewhere here, let's say this was the image. Let's say this is A double dash. Okay, no problem. If this is A double dash, this is B double dash. And I had to measure the distance of this image. Now, can anyone tell me, will this distance, let's say this is V2, this is V1, will the distance V2 be positive or negative? It will be positive. Prashna understood this. It will be positive because we have to measure this from the optical center to this point. So we are going along the direction of light. Light is moving this way. We have to measure it that way. Am I clear? So what I did was, I think I made a small mistake here with this positive. I think what I did here is, so we have to measure all the distances from the optical center. So I think that is the case. Yeah, we have to measure all the distances from the optical center. So the object which is placed here will also be negative. That was my mistake. Okay, so only thing you need to be aware of is distances are measured from the optical center. You have to start measuring from the optical center. Okay, so even this object cannot be measured from the object to the optical center. It has to be measured from the optical center to the object. So when we are measuring from the optical center to the object, we are going against the direction of light. Light is going this way, right? We are going against the direction of light, and that will be negative. Okay, now if we had an image somewhere here, this AB, this one, we are going along the direction of light. So we are going along the direction of light while measuring the distance, because we have to measure from the optical center. So this distance will be positive V2. This distance will be negative V1 because, again, we have to measure the distance from the optical center to the object or the image. So for this, we are moving this way. So if you are moving this way, this will be negative. Okay. So if you're moving against the direction of light to measure the distance, that distance will be negative. If you're moving along the direction of light for measuring distance, that distance will be positive. Am I clear? Prashna and Jia, am I clear? Okay. Okay. So we'll just do one case study, and I'll just ask you some simple questions, then we'll leave the class. So this is a convex lens. This is the principal axis. This is the object, and let's say this is passing through the focus now, and something like this happens, and we have an image here. This is AB. This is A dash B dash. You don't need to worry about how these rays are meeting and all these things. This will be done when this topic comes into play. I just want to ask whether you have understood the concept properly or not. Suppose now this is your object distance. Let's say this is U. Okay. This is your image distance. Let's say this is V. This is your object height. Let's say it is H1. This is your image height. That is H2. Now I'll ask serially, will U be positive or negative? Yeah, all of you said negative. It will be negative because we are measuring against the direction of light, right? Light is moving this way, and we are measuring from the optical center to the object. Correct. Will this height H1 be positive or negative? True. It will be positive. Everyone got it correct. This will be positive because we are measuring above the principal axis. Will this height be positive or negative? It will be negative. Correct? Because we are going below the principal axis. This V image distance, will it be positive or negative? Amazing. So I think you have got the concepts. So basically, I'm ending the class here. I will just turn off the recording, and you can ask doubts to me by unmuting yourself. Okay. I'm stopping the recording.